All right, so today we're going to go over forces and how to actually label all the forces that are acting on an object, which we call a free body diagram. So first, up until now, you've probably, whenever you're doing problem solving, perhaps you write your given information, right, using the grass method, and maybe you even draw a little picture of what's happening. Those pictures we call system diagrams, right? Kind of like the one below. What we're going to do is we're going to draw free body diagrams, right? And you can also draw system diagrams. I think system diagrams are great. It gives everybody sort of the big picture of what's happening in the problem. But free body diagrams are also important because they specify a single object and also what forces act on that object. Because if we're going to predict the object's motion, we need to know how it's being pushed and how it's being pulled. Okay, and very important, we only label the forces that act on that object, not the forces that that object pushes on other things. Right? What I mean by that is if you're looking at two people doing a tug of war, and let's say you look at person A. Person A is being pulled by the rope in one direction. That's all we care about. We don't care that person A is also pulling person B. We only care what's happening to person A, not what person A is doing to others. Okay, so we'll go over some examples. And there's also different forces that we can write on that free body diagram. One of them is called the applied force. So if you have, say, an actual person either pulling or pushing on something, we call that an applied force. Right? So in this case, we have this boy pulling on the cart. So we're going to write that. We're going to write it as a vector because force is a vector. So we're going to write the direction that that boy is pulling on the cart, and we're going to label it the applied force. Okay. Another option is tension. Okay, now actually we should probably label the boy as being our tension force because he's pulling it with a rope. So whenever we have like a rope or a chain or something and you're pulling on it, there's tension in the rope. Okay, so we call that the tension force. So we'll write tension force. And sorry, this applied force will be the girl pushing forward, for example. Then we also have the normal force. Okay, before I get into the normal force, I want to actually write something else first. There, gravity. Okay, gravity is always going to be on every object, at least on the Earth, right? And it's going to be pulling down. So if gravity is pulling down, let's say I have a book on a table, right? Gravity is pulling it down, but there's a reason why it doesn't continue to go down. It's because the table's pushing back on it. And the table's saying, no, I'm not going to let you go down anymore. Okay, that contact force between those two objects is called the normal force. Right? We write it Fn, and the normal force will always be perpendicular to the surface it's in contact with. So if you have a book on a table, the normal force is going to be up. But I could also be over here leaning back on the board here. And therefore, there's a contact force between me and the board. And so that normal force being perpendicular to the surface will be pointing outwards. But since I'm also standing on the ground, in this case I have two normal forces. One pushing up from my feet and one pushing out from the board. Okay, so that's what the normal force is. You can think of it like a contact force. All right, and if our object is moving to the right, in this case, right, there's always a frictional force. Right? Frictional force always wants to oppose motion. And so friction will always be in the opposite direction of motion. Okay, for the cases we're going to look at anyways. Okay, so we draw an arrow going in the opposite direction that's moving it, and we label it the force of friction. So in that case, those are all of our forces. Here's our system diagram. I should do this up here. Here's our system diagram, which is showing what's happening. But here's our free body diagram, which is showing all the forces that act on, in this case, the wagon. Right? We have our tension from the rope that the boy is pulling. We have our applied force because the girl is pushing it from behind. We have gravity pulling it down. The normal force, right, opposing, in this case, opposing gravity. It's that contact force with the floor. And we have our frictional force opposing the motion of the cart. Okay? To really understand the motion of the cart and what's happening, you need to understand all the forces that act on the cart. Now gravity, we can actually calculate gravity. The force of gravity is related to the mass of an object. Okay, but very important, force of gravity and mass are different things. Okay, we've learned what this big G is, small g, right? The acceleration due to gravity. Okay, it's also called the strength of gravity, or the gravitational field strength. And it has a value of 9.8 meters per second squared. It also has equivalent units of newtons per kilogram. So that's a constant everywhere on Earth, okay, for the most part. As long as you don't climb to the top of Everest or something, it's going to be about 9.8. Okay, and to figure out the force of gravity, you simply take the object's mass and multiply that by 9.8. Now, very important, I know when we like to think about the mass of objects, we tend to think of things in pounds. Right? I don't know why I always think of things in kilograms. In fact, I know my own weight in kilograms, but I don't know what I weigh in pounds. I know it's different from everybody else, and I'm getting a lot of weird looks. You're crazy, Mr. Meshi. Okay, but another thing I want to point out is the word weight. Right? When you say something weighs a certain amount, you're thinking, is it heavy or is it light? So if I'm trying to lift a refrigerator, I might say, ooh, that's really heavy, so it weighs a lot. Whereas I'm trying to lift an empty box, right? You're going to say, ooh, that is very light. It doesn't weigh very much. And because we say that, we tend to associate weight and mass as being the same thing. But that's not true. Right? Imagine trying to lift something that's heavy underwater. Suddenly it's lighter, isn't it? But has its mass changed? No. The mass is the same. Okay? Now in that case, the weight is the same. It's just the buoyancy force is helping you. But I mean, we can take that object into space. You probably don't have that experience, but you might be able to visualize, oh, you can go into space and like have 500 kilograms, and like, yeah, woo, with your fingers and pushing it down. Right? That's why you don't usually use weights in space to exercise. You usually use things that are like springs, right? So that astronauts can get their exercise. Okay, so in physics, weight is the same as the force of gravity, not mass. Right? And any force has the units newtons. So usually when you go to your doctor for a physical and they say, like, what's your weight? Has it changed? And he can say, no, it's still about 700 newtons. Right? But in English, we don't do that, right? We say, no, it's 70. Everybody says pounds, okay? It's just me that says it's 70 kilograms. Okay? But at least kilograms and pounds are both units of mass, right? And that's technically what we should be asking. Although, I don't know, maybe it sounds kind of rude to say, what's your mass? Right? But it's technically to be correct, that's the question we should be asking, not weight. Right? Otherwise, you can go to the moon where G has a value of 1.6 instead of 9.8, and your weight has suddenly decreased. But that doesn't mean you've been on some super diet. It just means you went to the moon. Your mass is the same. Okay, so that's a big difference that usually takes a while to get everybody's head around. And so I'll like sort of quiz you on that a couple times in the next few weeks. Next thing I want to talk about are internal and external forces. And when we draw free body diagrams, we only write the external forces that act on an object. Why do we do that? Well, you can imagine I'm on this chair with wheels. And if somebody came up and pushed me, I would move. Okay? However, if I'm over here and I'm trying to push myself, I don't go anywhere. Because these are internal forces. This is your free body diagram. And if I'm trying to push myself, right, they don't affect my motion. And we'll talk about why later. But I'm sure you can imagine trying to push yourself on the chair. It's not going to work. Now, if you use your feet and push yourself using the ground, that's different. Right? It will make more sense when we look at Newton's laws, because when you push off of something, it pushes back on you. Right? And that's why you move. So that would be an external force. In this case, well, a sort of normal / applied force. Right? But sitting here trying to push yourself, doesn't matter. Okay, so internal forces we do not consider on free body diagrams. All right, so we're going to practice with some free body diagrams. All right, so let's go over question number 1. Question number 1 is just practicing to draw a free body diagram for different situations. So for A, we have a cup sitting at rest on a table. Now the good thing about free body diagrams, or at least good for me because I suck at drawing, is every free body diagram, no matter what it is either a dot or a square. And so I tend to do squares. So we have, here's our cup. It's a perfectly looking cup sitting at rest on a table. So first of all, we're going to have the force of gravity acting down. So write down Fg. Right, now if it's at rest on a table, you have that contact force pushing it up. And that's what we call the normal force. Right? And that's all the forces we have in that case. Nobody's pushing it. Nobody's pulling it with a rope. Because it's not moving, there's no friction force there. So in that case, those are the only forces we have. Normal force is, it's a good question. Normal force isn't always opposite to gravity, but it usually is. I can give you a quick situation right now where the normal force is not opposite to gravity. And that would be, let me draw an incline. So we have a ramp. Let's put an object which is sliding down the ramp. Okay, in this case, gravity is always straight down. Right? It's never to the side. I mean, I never drop my pencil and have it fly sideways to the board. It's always going to be straight down. Okay? Now, the normal force is always perpendicular to the surface it's in contact with. So in the first one, the surface in contact was here. And so it's perpendicular to that, going straight up. In this one, this is the surface. So perpendicular to that is like this. Okay? So whenever you have something flat on a table, yes, it will be opposite to gravity. Okay? But it's not always going to be opposite to gravity. All right, so let's try B. A baseball player is sliding to the left across the ground. So I'm really good at drawing baseball players. There's my baseball player. Okay. Now, again, he's on the ground. So we're going to have a normal force. And we're going to assume the ground is level. The baseball field is level. It's not inclined. Right? And of course, we also have gravity down. Now, because he's sliding to the left, we have a frictional force opposing that. So we're going to have a frictional force in the opposite direction to the right. Now, a lot of times people want to say, well, if he's moving to the left, there must be a force to the left. And I get a lot of students writing it a force of motion or a force of movement or a force of, I don't know, something. There is no force of movement. We'll get to this later, but forces cause a change in motion. They cause an acceleration. They don't cause velocity. So if something's moving to the left, it does not mean there must be a force to the left. If you look at a baseball player sliding to the left, that baseball player is slowing down, not speeding up. Right? That would be weird if you slid and then suddenly your speed increases. Right? You slow down. Because you're slowing down, we have an acceleration in the opposite direction of the motion. And therefore, we must have a force in that direction. There must be a force in the direction of acceleration, but not in the direction of motion. So in this case, those are all the forces we have acting on the baseball player. Okay. Let's try C. A desk that is pushed to the left across the floor. Okay, I'm good at drawing desks too. There we go. Now if it's being pushed to the left, that's an applied force. So let's write an applied force to the left. And if it's moving across the floor, we have a frictional force countering that motion. Now since it's on the floor, we have a normal force, and of course, always have gravity pointing down. So there are the forces there. Let me just pause before I'm... Alright, so D, we have a large trunk is pulled by a rope tied to the right side. So here's our trunk. Okay, we have a rope right on the right side, and it's being pulled. Now, since it's a rope, we're going to call this the tension force. Okay, but again, I've seen a lot of people write it as an applied force, and you're going to calculate the same results, whatever you call it. Okay, now, of course, it's going across the floor. This actually, the question is cut off, but it should say the floor is rough, and the trunk does not move. Okay, so the floor is rough and the trunk does not move. So we have a tension force. Okay, of course, we're going to have gravity acting down, and since it's on a floor, we're going to have normal force acting up. Now, if you just look at that diagram, there's only one force acting to the right and nothing opposing it. So you would think, well, that would mean it should change its motion to the right. It should accelerate to the right. And I'll explain why that is later. But since it does not move, there must be something this way. Okay. And we'll do a lesson later on friction, because there's actually two types of friction. One that always opposes motion, and another that opposes the start of any motion. Right? And I'm sure you've noticed if you try push like a fridge across the floor, it's hard to get it to start moving. Right? But once you do get it moving, it's a little bit easier to keep it moving. And so we have those two types of friction. One which acts when two surfaces are actually moving against each other. And the other, right, when they're sort of locked together and it's hard to get them to start moving. So I'm just going to write this as a frictional force, and in a later lesson we're going to go into much more detail between these two types of frictional forces. I'm just going to... Alright, so now that we've drawn all the forces that can act on an object, we're going to talk about another term called net force. Net force is simply adding all the forces that act on an object. That's all it is. We say the net force is the sum of all forces, and we label it F underscore net. Okay, so that's the net force. And the net force is important to help us understand any change in motion. So for example, I could be sitting here, and someone can come and push me on this side, and I'll move here. Force causing motion. However, if one person comes over here and another here, and they both push on me from opposite sides with the same force, I'm not going to move. So it's important to understand motion to consider all the forces that act on you. And since forces are a vector, if someone was pushing me this way with 10 newtons and this way with 10 newtons, those vectors would add to 0. And therefore the net force would be 0, and you'd be able to say, yeah, that makes sense. You're not going to move. Okay, so net force is very important. And we've added vectors before. We've added, for example, displacement vectors, right? Sometimes velocity vectors. Now we're just going to add force vectors. So here's an example. So let's say we have this weight, and if they're holding the weight above their head, well, we're going to have some normal force, or you can call that an applied force as well if the person is holding it up there, and some force of gravity. Now looking at the free body diagram, if I were to tell you that the normal force is 1.6 kilonewtons, or a kilo, remember, is just 1,000, so 1,600 newtons up, and gravity is 1,600 newtons down, well, that just adds to 0. And it makes sense if someone's just holding it there in place. Right? The motion is not changing, it's at rest there. Right? The net force should add to 0. So let's do some more examples. We'll start with number 2, and then maybe we'll take a little break because I know this lesson is long. In this one it says, if the following objects are at rest, what is the missing force on each free body diagram? Would your answer change if the objects were moving at constant velocity? So let's look at the first one first. We have to find the missing force. In that case, here we have a force here. Right? It says a force of gravity. So we need to figure out what that force of gravity is. I mean, without writing equations, we can probably see, well, we have 12 newtons up and 8 newtons up. So 12 plus 8 is 20. That's 20 newtons up. If this is at rest, you would say, well, gravity must be equal but opposite to that. So it must be 20 newtons down. Now doing this mathematically, we would write that net force, F net, adding up all the forces would be 12 newtons up plus 8 newtons up plus whatever gravity is. Right? And gravity is acting down, and it should all add to 0. Should add to 0. Right? So 12 plus 8 is simply 20 newtons up plus whatever gravity is down. Right? And that should all add to 0. Now I can bring one term to the other side, but first, before I do that, I want to notice something. This is up and this is down. Now, whenever we added vectors, we always said, oh, you can't add an up and a down. We have to do something first. So for this down, I'm going to change it to up. In order to do that, I need to change the sign that is attached to it. So I'm going to write 0 equals 20 newtons up minus gravity up. You're not really saying that gravity is acting up in this case, because negative up is the same as positive down. So you haven't done anything weird with the laws of physics. But if we rearrange this equation, this term for gravity we can bring to the other side of the equation by adding it to both sides. So if I add gravity to both sides, I'll get it on the left side of the equation as a positive value, okay, which equals 20 newtons. Okay. Now what I've actually solved for, since I have the directional property there, I've solved for the magnitude of gravity. The magnitude of gravity must be 20 newtons. And the direction we know is down, which makes sense, right? It's what we thought of previously, right? If we have 20 newtons up and it's not moving, gravity must oppose it with 20 newtons down. And that's just me figuring it out algebraically. Now in the second question, we have two forces that are unknowns, this one's and this one. Now here's the trick. It sounds like it would be a problem. But what we're going to do is we're going to think of our horizontal forces and our vertical forces as completely separate. Anything in the horizontal direction does not affect anything in the vertical direction. And you can try to imagine how that would make sense. I mean, if somebody pushed you horizontally, you wouldn't cause them to go up, right? Whatever horizontal force you push on something does not affect anything in the vertical direction. Similarly, if gravity is pushing you down, you're not going to suddenly feel like you're being thrown to the right. Okay? Anything that affects vertically does not affect horizontally. So we can consider them completely separate. So let's look at it just qualitatively without any equations. If we have 22 newtons down, this normal force, which is in the opposite direction, must have the same magnitude. So it must also be 22 newtons. It's just in the opposite direction. It's going to be 22 newtons up. Now if we're looking at the horizontal portion, for the horizontal portion we have 28 newtons to the right, and we have 15 newtons and some unknown to the left. So you can think of it, again, as all your forces acting to the right must equal all your forces acting to your left. So I can write this down in a simpler equation. I can put all my left forces on the left side of the equation, just without any directions even. Say 15 newtons plus that frictional force must equal to the magnitude that's being pushed on the right, which is 28 newtons. Okay, that's the same thing as saying the net force equals 0. Right? We're setting all of our forces, or the magnitude of those forces acting to the left, equal to the magnitude of those forces acting to the right. And then we just rearrange the equation. If we want to solve for this frictional force, we're going to take this 15 newtons, which is being added, and subtract it from both sides. So our frictional force will be 28 minus 15, right? Which will equal 13 newtons. And in our case, it's to the left. All right, so good question. Because they're at rest, all the forces add to 0. But the second question says, would your answer change if the objects were moving at constant velocity? And the answer is no. The reason is forces cause a change in motion. I said this before. Forces do not cause motion, they cause a change in motion. So even if you're moving with a constant velocity, the net force acting on you must be 0 because you're not accelerating. Right? Forces cause an acceleration or a change in motion. And so if you're on the highway moving at 100 kilometers per hour south, and you continue to move at 100 kilometers per hour south, then the net force acting on your car must be 0. Now, there's lots of forces acting on your car. Sure, you have an applied force forward due to the engine causing the tires to rotate, right? And then you'll have forces opposing your motion, like, say, the drag force, like wind pushing on your car and things like that. But if your speed, your velocity is not changing, all of those forces add to be equal but opposite, which causes the net force to be 0. All right. Question 3, here we have 2 children are fighting over a toy. One pulls with a force of 20 newtons east, and the other pulls with a force of 5 newtons west. First, we're going to draw a free body diagram of the toy, and then we're going to find the resultant force, or net force, acting on it. Right? So there's the toy, right? And it says we have one student pulling 20 newtons east, so I'm just going to write 20 newtons east. And the other one, now usually on a free body diagram, if the magnitude is a lot smaller, then the length of the arrow should be smaller. So in this case, you can clearly see this arrow has more force than that one. And that's 5 newtons west. So there's our free body diagram. Now, if you want, you can add the gravity and normal and what else, but in this case, we're not going to, because they're not really going to help us answer the question, because they're going to just cancel. Right? Remember, everything acting in the vertical does not affect anything in the horizontal. So to figure out our net force, we're just going to add these 2 forces. We have 5 newtons west plus 20 newtons east. Now again, you can't simply add 20 plus 5 because one's east and one's west. So what I'm going to do is I'm going to change west, since it is the smaller number, and I'm going to make it negative 5 newtons east plus 20 newtons east. Right? Now you can simply add them. So 20 minus 5 will get 15 newtons east. So that's our net force. All right, so last question in this lesson. Here we have a clerk pushes a parcel towards a customer with a force of 7.6 newtons. So let's sort of draw this as we go, because this is a wordy question. So it's pushing, right? So we're pushing, so that's an applied force, and it's east, so we'll write our applied force equals 7.6 newtons east. The frictional resistance on the parcel is 6.5 newtons west, so let's write a frictional force of 6.5 newtons west. And both the force of gravity and the normal force have a magnitude of 9.9 newtons. So we have gravity down and normal up, 9.9. Okay, so draw a free body diagram. Awesome, we did that already. And determine the net force. All right, so when we have forces both acting horizontally and vertically, when we find the net force, we're just going to do it twice. Once for everything horizontal and once for things vertical. Because I've taught you, for example, how to change west to negative east. But you can't change, for example, this would be very careful. The normal force is not north, it's up. Okay? Think of it more as a 3D diagram, and this is down. Because north is not the same as up, right? If that's north, that's not up, right? And so gravity doesn't act south, because that would be south, right? But gravity acts down. Okay, so it's sort of a three-dimensional picture. Oh, I got. So what we're going to do is we're going to consider our vertical separately. And so let's look at our net force acting vertically. I'll call that y. It's because when you do a Cartesian plane, y is up and down. So we're going to call that y. Right? And in this case, we have 9.9 newtons up plus 9.9 newtons down. Now you can probably see this is just going to add to 0. Right? Which makes sense, because if it didn't add to 0, let's say it added to 1 newton up, then that means it should be taking off, right? Because it should change your motion in the vertical plane. Now if we also looked at separately our net force, our horizontal one, because of the Cartesian plane, we'll call this x. Here we have 7.6 newtons east plus 6.5 newtons west. Right? We add those together. We have to change west to negative east. And I choose to change this one because it's the smaller number. Right? You could change the other one. You'll get the same answer. You'll just get a negative answer. Right? You'll get negative west, but in our case, we'll get positive east. That's the same thing. So we have 7.6 newtons east minus 6.5 newtons east, right? Which gives us 1.1 newtons east. Okay, I'm going to stop it there.